Roughly 60% of patients with epilepsy suffer from focal seizures. These are localized events characterized by excessive and unregulated amounts of activity. It's important for neuroscientists to understand the conditions in the brain and how they lead to different activity states like these focal seizures. Experimental research has yielded a wealth of data at the level of single cells, but understanding what this means in the context of larger collective behavior often requires the use of mathematical modeling. Now, building a good model, a set of equations that mimics the real system, still requires a language for discussing what the model is doing. And when you have a system with many interacting pieces, like in the brain, this is very hard to do. To address this, I use tools from theoretical physics and information theory to build a language for studying the statistical behavior of network models at the level of populations as you adjust these cell-level details. The models I study begin with a single equation for each cell, these smaller red and blue circles here. We connect them together with these green arrows to form a network. And we can tune two different cell properties in this example, the resistance of cells to incoming signals and the strength of the signals that they send out. The first step of the analysis, I group these together into populations of interest. Here, the red population and the blue population. I next approximate the behavior of the population as an average and some variability around that average. And we study how these statistics change as you tune your two cell properties. Now, if you tune the resistance very low and the signal strength very high, you get a state in the network where both populations have excessively large average activity. We can think of this as the appearance of a focal seizure state in this model network. The variability in the behavior around that average changes even more drastically as you tune these two controls, giving you some states with extremely low variability and some with extremely high variability. We can picture these high variability states as giving the network more behaviors it can choose from, which is good if it has to do many different tasks, but is very bad if it has to do one thing consistently and precisely. Moreover, the type of activity that we see in the network changes most significantly as you adjust the ratio of these two properties. This gives us a high-level insight into how the resistance of the cells and the strength of the signals they send interact with each other to change the state of the network and can even lead to events like these focal seizures. Taking a step back, I'd like you to walk away with this. Sometimes when we want to study big complex models, systems, we need big models. And to study big models, we need the right language to talk about them. Thank you.